Today's first talk will be by Constanze Roitzheim on continuing the talks on chromatic homotopy theory.
Well, thank you very much. Was it that terrible last time? Just feels like teaching at home, I want to say. That's like the Friday morning, 9 o'clock slot, probably wouldn't be very popular there either. Anyway, because I also wanted to answer a couple of questions that I was asked last time. I don't know if the people who asked are even here. So we continue towards our goal of studying the stable homotopy category. And we did so, we introduced our most important tool for that last time, namely e-localization. So when you pass from the stable homotopy category to the e-local stable homotopy category, we did so by formally adding making the E star isomorphisms actual isomorphisms in here. So rather than just inverting those maps of spectra formally that induce you an isomorphism of homotopy groups, we now also invert all the maps that induce you an isomorphism of homology groups for whatever homology theory you picked. And well, we had all the various definitions for that last time and how that worked and why that worked. And we also studied, so the examples we studied last time. We did rationalization. We did p-localization. And we did p-completion. And these two had very nice technical properties. This one, not so much, but they all have their various technical advantages and disadvantages depending on what it is that you would actually like to do with it. So, for example, these two had the properties that localizing was just the same as smashing with the local sphere, and this one did not. So, for example, in the rational stable homotopy category, two things will be isomorphic. Well, something is an isomorphism if it induces an isomorphism of rational homotopy groups. Here, if it induces an isomorphism of p-local homotopy groups, but here it was a little more complicated. So one of the questions after last time where I had just too many options buzzing in my head was if you take, let's do it up here, if you take an exact triangle here, is the triangle made out of the respective localization still exact? And well, the answer is yes, because this functor here is induced by the identity as a left Quillen functor, and left Quillen functors are exact. So localization preserves exactness. But there was another exact triangle that was important because you could of course, one of the axioms of exact triangles was that you could take any map and complete it to an exact triangle. So I could write any x to y here and then put a suitable third thing there, and that would be exact. And in this case, if you pick your map to be the E localization, your co-fiber would be called CE of x. And yeah, then you get an exact triangle like so. Why am I saying that? I'm saying that because this one then has the property that this is going to be an E acyclic spectrum. Because if you take W to be an E local spectrum, and then you apply the functor of maps into W, you're going to get a long exact sequence. It's going to go all the way around, of course. And because this one is local and this map here in the first argument is an E equivalence, you get an isomorphism here. And because it's a long exact sequence, this one is going to be 0. So for every x, you can make a corresponding local object, and you can also make a corresponding acyclic object. Why am I actually telling you that? Well, in a little while, we are going to see an example where we will use that two localizations are the same, not only, well, either if their local objects are the same, but you can also say that two local objects are, two localizations are the same if their acyclic objects are the same, because they just fit into these exact triangles. And if you have the same acyclizations, you also have the same localizations. And I just thought that would be a good thing to remark on because we're going to get this later. Right, but what we really wanted to do is define other homology theories E, which will help us really get deep inside of this. Because these ones are very nice. They help you with some calculations, of course. If you want to calculate stable homotopy groups of spheres, for example, you would certainly come across these ones. This one has all its own fun and features, but if you really, really, really want to get to the deeper structure of this, you need a little more. So one of the features of Gauss-Witt localizations is that it kind of throws away information. This you can already see here quite well. If you rationalize, you throw away information. It's just like as if you're putting a black and white filter on a photo. You don't see all the things that you saw before. But if you're picking your homology theory well, depending on what it is that you would like to do, then maybe you can see things better than before. It gives you the opportunity to just throw away redundant information, get rid of some noise that you don't want to see. And the theories that I will come back to, they will be quite a powerful machinery to do that. And yeah, I am a bit worried to do that, to be honest, because I'm not sure if you were really big fans of them when I first wrote them down, but it's okay. They're friendly. They are. So let's summarize that story again. We started with mu complex cobordism. well, I barely know the definition of a manifold, but it is a homology theory, a cohomology theory to do with geometric things. But when one then goes to Brown representability and looks at the spectrum and all kinds of properties and calculations, people like Quillen and also Adams extracted that this one really is very universal in the sense that a lot of constructions can really start from there. And so I will be writing down a lot of coefficient groups just because it is not easy to understand the constructions and properties that arise in topology, and kind of looking at the coefficient groups and how they change and how they are related is really the only way to make things visible. So mu star, which is another word for pi star mu, was this lovely integral polynomial ring in infinitely many variables. And when I wrote this, I meant the degree of xi. I have absolutely no idea why in other talks people would have written things like little circles around it, but that's how I write degree. I mean, it's a question of personal taste, isn't it? But people were confused that that meant degree. I thought that was not such a non-standard thing, degree. Maybe I should have written deck, but now you know. So, and just as an infinitely dimensional polynomial ring is a good algebraic object because you can map into anything you want, this spectrum was universal in the sense that all the constructions you can do with this ring, you can kind of already do with the underlying spectrum, and it will induce you all the algebra you would like to do. But we also said from now on, everything is going to be p-local because, I mean, now that we know how to p-localize, why would we put ourselves through the effort of carrying around all pre-primary information for all primes simultaneously? We're just going to localize at a prime. And then, of course, this spectrum also becomes far too large to be bothered with. And the p-local mu split into various copies of shifted shifts of a spectrum called BP, where I still haven't looked up the indices, but Google wasn't that friendly to me. And the coefficient groups of the BP are similarly nice. Also polynomial ring with infinitely many variables, with generators of a degree. That is now a bit funny. So probably from that I could work out what these indices are. But that is kind of going to play the role of our p-local mu, because for many things, it doesn't really matter if you take just one copy of the BP or the whole lot, because if you would like things to see detected or discovered by BP, it makes no difference if you take one copy or lots of it. So we are just going to be working with this thing. Yep, and from this BP, one can then apply co-fiber sequences and telescopes and all kinds of constructions like so to get to homology theories, En and Kn, and the coefficient ring of En was at least a little bit smaller. So it goes to Vn, but then you have to invert the last just the last Vn, and then the coefficient ring of Kn looks a bit friendlier to begin with, but believe me, that is the naughty one. That's the friendly one. These are the coefficient rings of these. And then rightfully, I mean, I didn't really get it so much as a direct question, but I could see it in people's faces saying, like, why? Why would you do this? Why these things? Well, of course, in the course of this talk and the next, I will hopefully convince you that that was the right thing to do. But some decades ago, when people started doing constructions with BP, it was not necessarily clear that these would be the things that come out of it that are the survivors, because even if you go, so one of the key papers, I would say, is Ravenel's 1983 paper, localization with respect to certain periodic homology theories. And if you look into that, there are lots and lots and lots of different spectra with different letters. There are MNs and CNs and capital letters and connective versions used to prove certain theorems. So it's not just clear that somebody looked at the BP and said, oh, let's do something to get exactly these things. There are lots and lots of others, but over the course of time, these ones are the ones that emerge to be the most kind of visibly useful ones in the theorems that people use as the basis for modern chromatic homotopy theory. Okay, but while there's still lots of ends and stuff, let's just start somewhere smaller. So what about n equals 0? It's always just good to start at n equals 0, isn't it? Start with the smallest possible version of it. Well, now if you're looking at that, what would that even be if you picked n equals 0? Well, the convention is, the hidden convention is that V naught, well, is considered to be P. So it's in here without you necessarily having to say that. And therefore, if you are here and you're here and you formally invert your P, the convention really is that E naught and K naught is just HQ. So taking well, if we said we would like to localize with respect to E naught or K naught, it is just rationalization. And so we've done all that and we still haven't done anything new, have we? So let's get to n equals 1. That is also not necessarily something new, but at least I think it does a better job psychologically than this one, anchoring the first non-trivial level of chromatic homotopy theory in something kind of classical. So both E1 and K1 are very strongly related to topological K theory. Not algebraic K theory. We've seen not really too many Ks, but you see math has a problem with not having enough letters, and we had Ks to be the homotopy category of chain complexes. We've had Ks to be causal complexes. K is also algebraic K theory, and now it's also going to be topological K theory. How do you feel about the idea of introducing more different alphabets into math? that good? Because it was a very fashionable thing when I was a student, or rather, one of our professors, Carl Friedrich Bödichheimer, he loved to use Gothic scripts to just add more letters. And when people looked absolutely scandalized, he said, this adds color to your life. And I think it's great to use lots of different alphabets, but it's kind of, it seems to have gone out of fashion recently, especially with teaching, because I think our students just couldn't handle it. I mean, even Greek letters, like rose, not easy. So I'm very bad at size. Thankfully, I never really have to write any. So topological K-theory, very geometric in some sense. So you start by defining a cohomology theory by looking at of spaces, by looking at vector bundles on these spaces up to a certain notion of equivalence, and then completing this using the Serre construction to some kind of ring. But you don't actually have to know any of this. K-theory has a representing spectrum, and we're going to use that representing spectrum. However, when I say K-theory has a representing spectrum, there are already two kinds of it, namely you can look at real vector bundles or you can look at complex vector bundles. So there is KO, which is real K-theory, and there's KU, which is complex K-theory. And well, we're still working at P, but we don't actually really even need the P. And these are, of course, different spectra. They are by no means weakly equivalent. If we look at their coefficient rings, this one is, which letter did I give it? By what periodicity? It is this. That one I can't remember. It's 8 periodic by real Born periodicity. It has some Z's and some Z mod 2s in it and stuff. So you can see that these are not really the same spectra. So if I'm saying, oh, I would like to K-localize, what do I even mean? And the first real good news of the day is it doesn't really matter, because while these two homology theories are absolutely not the same, localizing with respect to them gives you the same thing. And why is that? So both KO and KU do us the favor of fitting into the following exact triangle. So there is an exact triangle like so. Fine. What's the map? The map here is identity of KO / eta. What do I mean by that? Well, suspension of KO is the same as S1 / KO. Now I've written it the wrong way around. That is, of course, just 0 sphere / KO, and eta lives in the first stable homotopy groups of spheres. So that's just a fact for you. It's not just one element of the many, many, many. It's also the very most important element of all stable homotopy theory, but that's just a side note. You could take KO and smash it with eta here, and that fits into an exact triangle like so. So now I can also smash that with X. So if I now smash that with X, I get take any spectrum X, I can smash it and still have an exact triangle. And then you can already see, of course, that if KO smashed with X was trivial, then, well, you would have 0 here, 0 here, 0 here. And by the axioms of exact triangles, this one would have to be 0 as well. So if, in other words, if X is KO acyclic, then X is also KU acyclic. So that's good, but we would like to have an equivalence so that we can also say that they have the same localizations. Well, I mean, how much do you remember about stable homotopy groups of spheres? I'm not saying can anybody tell me what pi 12 is or anything like that, but structurally, whatever I wrote here, whatever Greek letter, eta, nu, or sigma, or rho I wrote here, they will all have one thing in common. All the elements are nilpotent multiplicatively. So why care? Well, if I had that X was KU acyclic, then, well, I would have something trivial here, and therefore I would have an isomorphism in the other spot. Let me just write eta, not smash all the other stuff. So now, even if our knowledge of algebra is very, very basic, mine certainly is, can something be nilpotent and an isomorphism at the same time? Oh, at least shake your heads. It can't. So in this case, eta to the 4th power is 0. It doesn't even matter. It's 0 to some power. So smashing with other stuff to the 4th power would also be trivial. But you can't be nilpotent and an isomorphism at the same time. Unless, of course, this thing itself was 0. So that's what it would have to be. So the only chance it can be an isomorphism and nilpotent at the same time is if this one was just trivial. So which way around is it? This one implies this one just follows from the very existence of that exact triangle, and the converse follows from the fact that one knows a bit about this map here. Therefore, KO and KU have the same acyclic spectra, and therefore it must mean that their localizations are also the same in the homotopy category. So henceforth, it doesn't matter at all whether you pick KO or KU for your localization. I'm personally going to pick KU just because its coefficient ring is a lot simpler to deal with for any kind of calculations you'd like to do. Let me just write that down in a sec. Right. So I can just write, well, that's also true P locally. So I can just write K by pretending there's no difference. But that is not actually all. I said I would like to actually relate this to the E1 and the K1. Well, so remember that the coefficient ring of E1 is just, well, if I already start inverting the V1, then I get that. And that looks very similar to saying local P localization of the coefficient ring of K theory. But the underlying spectra still can't be the same because, well, this one has degree 2 and this one has degree 2p minus 2. So unless p equals 2, which I think is, of course, a perfectly fine place in life to concentrate on, unless p was equal to 2, these two things would not be the same. So, well, just for completeness sake, let's just write 1 star underneath so that you all have them together. So here you have Z mod P, and then this generator again. But very similar to how what I wrote down here, well, except that in this case, I actually know what the correct coefficients are. This one splits into several shifted copies of this, and that is down to atoms. And if you are interested in that sort of thing, I highly, highly recommend that you read it because it's really very, very nicely written. So if you take P local, there's also an integral version of that, but I don't need it. So if you take K theory of a space X, then that splits. So this cohomology group splits into shifted copies of something, some groups called G of X. So it splits into P minus 1 copies of a smaller cohomology theory. This G, I mean, speak of the overuse of certain letters in math. Does anybody actually know why it's called G? So-called atom summoned. Normally, whenever you see a capital G, you're so drilled to think, well, look, there's a group. But it's also just here on this board. It's called the atom summoned. And well, this, of course, has, because this is a cohomology theory in itself, it has a representing spectrum. And the representing spectrum of this, well, if we were consistent, we would just write G, but it is exactly what we would now call E1. So you can already see if you just took X to be the sphere, this splits into lots of shifted copies of that, and it's even the correct index. But yeah, also as a spectrum, this one splits into lots of shifted copies of this spectrum. And so therefore we can see that this is just E1 localization, And people are even lazier than that, and they're just calling that L1. And in general, we will see that EN localizations we will call EN. Yeah. So far, so good. So at least we can now talk about this arrow with a bit more confidence, namely that this one does not equal K-theory, but localizing with respect to that is the same as localizing with respect to both real and complex topological K-theory. Because maybe I should really say that as a remark. If you have a spectrum E that is lots of shifted, the other way around, lots of shifted copies of some F, and localizing with respect to E is always going to be the same as localizing with respect to F, because if you plug that into the definition of what it means to be local, you know, the thing with inducing isomorphisms of homomorphism groups, that's going to give you exactly the same. But, well, what about this arrow? Let's not forget that one. What about K1? Well, if you look at K1, well, what is true without this, we can see that that one is just this one mod P. I can do the same on the spectra. I can put multiplication with P on that spectrum and take the co-fiber or fiber and get that. So what we really have here is this. And so localizing with respect to K1 is therefore localizing with respect to E1. Smash this. And let's put an X here because it looks it's empty otherwise. So what that really is at least that's a nice localization. And there are various, should have done that now rather than later. Oh, what this therefore is you take E1 localization of X. This one was P completion. So what this really is, localizing with respect to K1 is localizing of what it's P complete K localization. And that just plays into the narrative that I tried to sell you last time, that P localization and P completion are really the toy examples for how the ENs and the KNs are going to work. And indeed, here we see again, this one is a very nice localization, and this one is some kind of completion. But we haven't actually really seen that it is a nice localization. So far, you have to take my word for it that this is nice. But because it's K-theory, and people have been studying it for a long, long time, thank goodness we know some things about it. One can do calculations with regards to it. And, well, I mean, depending on what your pain threshold is, they're even relatively manageable sometimes. So, just back to almost the beginning, when we said we start with a class of morphisms W that we would like to invert and form the W local model structure. One of the issues was always like, if it exists, because you can always localize at a set of morphisms, but not really as a class. When people want to localize at a class of morphism, the proof is almost always, let's find a set that generates me the same class. And so for E-localizations, to exist, there was, for the proof, there was a set JE such that localizing with respect to that set is the same as localizing with respect to all Easter isomorphisms. And generally, yes, some of you asked about it. The proof is still kind of, I find it complicated. I can't do it without practicing lots, and I didn't practice it. It is a lot of set theory, and even so, still complicated. With K-theory, however, you don't need a big and abstract map, a set of maps. You just need one. So that is in Adams's on the groups J of X. That one will come in part 4. And unlike stuff like the Fast and Furious films, you actually have to probably read 1, 2, and 3 to understand 4. So, but if you don't want all the absolute dirt on it, it's also summarized very nicely in Bausfield's paper on the localization of spectra with respect to certain homology theories. So let's take a look at that. So if we take M again to be the mod P Moore spectrum, then this has the very, very special property that it has a so-called V1 self map. Well, what is that? Well, for P equals 2, there is some map like this. For odd primes, there is a map like this. And what does it do? When you apply K-theory to that map, and you would, of course, get, well, when you, let's say we apply, we're modern now, we're chromatic. When we apply E1 to that, we would get a module over this. I can say exactly what it is because it's co-5 of multiplication by P on that. It will actually induce you a power of the element V1. And therefore, people just call it V1. In this case, it will induce you V1 to the 4 on K-theory. So people write just that. But it is not the 4th power of some other existing map. That is the smallest existing map that induces you some power of V1 on K-theory. So that is just kind of abuse of notation. But I will just pretend that we're going to be here, so that's going to be a bit easier. So in general, just as a side note, that is a reasonably big industry, as in, if you have that, and then you take the co-fiber of these, then you can see if that has a V2 self-map as well, and so on. So finding spectra, cell complexes that on which you have Vn self-maps is a very interesting structural property, because that is related to a lot of different things. And also finding the smallest possible such thing is also quite a big industry, because these will be related to a lot of actual horrible calculations with spectral sequences, which again feed into some important open conjectures. But anyway, for K-theory, one has that. And now, big theorem by Adams. Let me just write V for any of those, or let's just, I don't want to distinguish between those all the time. X is E1 local if and only if no, that's not X. If this V1 self-map induces me an isomorphism on, I mean, that's the mod P homotopy groups. So by the definition of being local, X would be E local if and only if for any E1 star isomorphism that I plug into the first argument, I get an isomorphism. That would just be the definition. But the theorem by Adams says it is in fact enough to check this on just one map only. Just this one map tells me if something is K-local or it isn't. So therefore, we could even write another thing if we really wanted to. We could just say it is the localization at just that one map. So if I go into the stable homotopy category and just invert V1, I get the K-local stable homotopy category. So you can imagine, for all kinds of purposes of what people want to do with it, this is a massive structural advantage and a big computational advantage as well. And in fact, it implies the famous telescope conjecture at the level n equals 1, that I'll certainly mention again next time. But it is like the last, well, it is the big open conjecture in chromatic homotopy theory for other n, and for n equals 1, it's true because of that. Okay. So one thing I might also mention at this point, but I'm afraid I won't be able to prove that, is K-localization is smashing. In other words, L1 of X is the same as X smashed with the K local sphere, K1, E1 local sphere, the K local sphere. So again, that goes back to the slogan that the ENs are a bit like P localization and the KNs are like completion. And this one has this nice property. So this really comes down to, this one is also quite computational and relies on things like that. So one would have to know what the homotopy groups of this thing are. There are also quite hands-on methods of constructing a K-localization of X using mod P to the N more spectra. So the calculations are quite big, but not nearly as big as recent research papers in chromatic homotopy theory tend to be. So they use very classical methods. They use lots of log exact sequences, diagram chases, that sort of thing. So I would say compared to many things that one could see in chromatic homotopy theory today, this is quite a friendly one. Yeah, but this is not just to kind of, well, one localization is not, well, I can't justify that yet, but it isn't. But so the point of looking at E1 and K1 wasn't just to say, okay, that one is a bit like P localization, it is a bit like P completion, but we also had the rational case. We had n equals 0, as we now know. And the point is that we're not just we don't just want to chop up the stable homotopy category into some En local bits and some Kn local bits, but they also have relations with each other. And how these work, we can see relatively nicely if we look at the relationship between these level 1 things and the level 0 world, which is rationalization. So let's have a look. Right. So and the thing is that if X is rational, that's a shorthand for saying it is its own rationalization, then X is K local. So being local for E naught implies being local at E1. And we will say later that being local at En will imply being En plus 1 local. And in fact, whenever I try and think about stuff, it's easy to get the direction of the statement wrong, and then you can always remember this one, because being K local obviously cannot be the same as being rational, because being rational would imply that all your homotopy groups are Q modules. So that's always the strongest, most hardcore localization you can have. Why is that the case? That's actually a very nice thing to write down. So if X is, I would like to prove that X is K local. So I would like to prove that that one just equals X again. But because it's already rational, I can write down that, which is just the same as that. And we also know that both localizations are smashing. So doing that is just the same as smashing with the rational sphere, and then again smashing it with the next local sphere. So I've just written down that you have a smashing localization or two smashing localizations. And then you can hopefully have a look at it, stare at it for a moment, if you can see it. And now we can look at what this is. So now again, if you knew what the stable homotopy groups of the K-local sphere were, you would know that actually, just as with a non-local sphere, all that survives of it is a copy of HQ in degree 0. And because X was assumed to be rational to begin with, that is just X. So the homotopy groups of the K-local sphere are about as known I need the homotopy groups of this. HQ is HQ. I know what happens when I smash this one with HQ and I just get HQ. Yeah. Well, but I don't know that yet. That's exactly what I'm trying to prove. So calculating the homotopy groups of this. It's a lot easier than calculating homotopy groups of the sphere, obviously, because that's horrifically different. But there are various ways of getting it. As a PhD student, I was made to sit down and do all kinds of different spectral sequence calculations to get as much of the atom spectral sequence E2 page, and therefore the whole thing enough in order to be able to prove what I wanted to. But I also got help from Mark Mahold when I visited the Max Planck. So my supervisor then said, oh, Mark Mahold is at the Max Planck Institute. You should go and ask him everything you want to know. I mean, I was 25. I was a not particularly confident PhD student, but that was offset by the fact that I was also really desperate to learn these things and to fill in the gaps of what I really wanted to know. So I went there and I asked him about the homotopy groups of the K-local spheres, and he explained it to me very kindly and nicely. And that was before, obviously, one had smartphones, so you couldn't just sneak a quick picture of the whiteboard. And I sat there and it sounded all very nice, and it made sense in the moment, you know. And then I got home and tried to recreate it, and there was absolutely no chance. So I did ask him, saying, can I please come back and you explain that to me again? And he said yes. And then I understood it at least as much as I needed to, and it was very, very useful. So if you're still a student, don't be afraid to ask people. I don't think Mahold ever had a particular reputation of being scary, but of course it's very easy to be impressed by someone who's a lot older, and in this case, an absolute legend. But yeah, if you don't ask, you don't get. And it's also nice to actually have some things to ask, because at the beginning of my PhD, all I really wanted to ask was, what is any of this? Yeah, so that is how I learned a lot about that. And therefore, I can also say with confidence that the only non-torsion homotopy groups of that are in degree 0. But you can also find that written out both for p equals 2 and odd primes in that Ravenel paper from the 80s, except that from Mahold, I also got the information what it just looked like in the Adams filtration, like what level certain elements appeared and so on. And if you like calculations, it is a nice thing to do, and it is not even that scary. So now at least we have a bit of an overview of En and E1 and K1 and the relationship with one floor down. So let's get to the others. It is not a surprise, I guess, to hear that if we go to E2 and K2, things are going to become a hell of a lot less manageable. I tried to do some E2 local stuff in lockdown. I mean, people do all kinds of crazy things in lockdown. But because there was a new paper out about a complex with a V2 self-map, so a lot of my PhD thesis hung on calculating things based on this. And previously, the smallest known V2 self-map on something had degree 192. So if you want to do calculations here and you have some exact sequence stuff, so you need to do homotopy groups in range, let's say 0 to 9. For good measure, maybe add another at each end, but that is still doable. But 189, forget about it. 192. And there was a new complex that people had constructed that brought this down from 192 to, anyone wants to guess? 6. That's a big step forward, isn't it? However, you never get anything for free, do you? So whatever you gained in less, having less of a range, the spectrum you would have to put there has a lot more cells. And so the complexity was now in the thing itself. So if you want to calculate something, it is still pretty much as complicated as it was before, even though the people who constructed that complex, I mean, they didn't do it for nothing. There are certain very, very specific things that people would like to do where this new one is actually better than what was known before. But this is just to say, if you're trying to calculate things at n equals 2, so I was very naive and I emailed to people in lockdown, people who are real experts on K2 local sphere, and like Mark Behrens, and I asked, is anything known about these things? I thought if I knew them, then I could prove something, and their emails responses were almost entirely like, no. So n equals 2 is very, very complicated. So what about higher n? So that doesn't mean that people don't try. So for n equals 2, just as E1 and K1 are related to K theory, well, they're actually much more than just related to K theory, but if you say n equals 1, people normally think, yeah, K theory. For n equals 2, one gets to something called elliptical homology theory. Of which I know extremely little, but Neil knows a lot more. So there are still certain things that, concrete things that people are trying to do at n equals 2. people are also still trying to calculate things. So, for example, this thing of when I said I try to calculate or recreate existing calculations of what the homotopy groups of the K-local sphere were. So I didn't put that in notes, so I'm probably going to get this horribly wrong. For n equals 1, there is one can think of, I just know it for 2. There is an exact triangle that the K1 locus, E1 local sphere fits in. It fits into 2 copies of KO, and here we put in an Adams map -1, which is basically multiplication by 8. And if you want to calculate this, if you do the Adams spectral sequence, you need to know what the cohomology of the input is as a module over the Steenrod algebra. People know this here. Yeah, that's 3. I think so. I'll write this down somewhere. If I say anything wrong, I will correct it next time. I didn't write it down at all. So why am I saying that in the context of this? Well, one could think of this almost as a kind of resolution of the sphere by other things. Or also you could think of that as kind of an action of this on KO, and therefore as that as some sort of fixed point spectrum of this. And one big business in chromatic homotopy theory is that people like Hans Werner Henn and Paul Gers and other people around them have tried to successfully try to generalize this for the K2 local sphere, I think. K2, not E2. So what people are doing at n equals 2 is write down resolutions of the K2 local sphere, and there are lots of open calculations because this very, very heavily depends on the prime that you would like to localize. But I think P equals 3 for this was one of Hans Werner's great breakthroughs back in the day, wasn't it? So, and people still work on these things. And whenever you see papers like that, they're normally huge, huge, huge atom spectral sequence calculations. And then again, more spectral sequences plugged in that calculate your E2 terms. And just in order to make relatively little progress in there, in the sense of, oh, let's try P equals 7 and see if we get it too. It is kind of almost a lifetime's work. So sadly, as I noticed, that's not something that you could just dip your toe in for a couple of years. This is something that you really need to commit a life's work to if you want to work at n equals 2, I found. And I'm very, very glad that people do. I'm very, very grateful that people do. And I hope that I praise their persistence, and I'm hoping that long may they continue with that. But generally, for higher n, one cannot be very, let's say, concrete or hands-on in any way. So P equal to 3 is definitely the most established of the cases. I don't know what the precise state of the art as of 2023 is. Certainly other primes have been attempted. I don't know how complete their efforts are. I think P equals 5 has been done. So if we can just say, oh, for n equals 0, it's rational, great. For n equals 1, it's K-theory, or that's also something we know. For n equals 2, it has relationship to some very nice algebraic things. And maybe if you want to spend your next 30 years doing calculations, you can also do them. But then afterwards, nobody knows. So why do we bother? Well, after that, it becomes a lot less about, well, what is the EN localization? What is the KN localization? What are the homotopy groups or anything like that? It becomes a lot more about their more abstract properties. They will become quite hands-on. So I hope that the word abstract doesn't put you off, but I think that ship has sailed a long time ago. It becomes more about the relationships between the different layers between each other, and some of the more categorical properties, and also some big results, big structural results to do with them, that I think already these days are considered classical. Let's talk in the coffee break how old something has to be for you to consider it to be classical, okay? And well, so that is where I think I would like to continue next Wednesday. And I look forward to doing that. Thank you very much.
Yes, thank you. Questions, comments? Okay. So
well, if you want to do any atom spectral sequence calculations for anything K2 local or E local, people just don't know the differentials. So a lot of things can be said, but never enough to get a complete picture, because at some point people will run into differentials in the spectral sequences that they just don't know. But there's every year there is new differentials, new attempts to go around them, so people keep working. Again, for that, I would refer to Adams's J of X, which is 4 volumes. So it's not that quick. Sorry. But I will think if maybe there is I will think for next time if there's maybe a good summary of how the argument goes.
Any more questions? Okay, if not, let's thank the speaker again.